Okay, chemistry students, this is lesson 4.3, and we're going to look at the next step in the evolution of the atomic model, the Bohr model of the atom. This would go with the reading in section 5.3 of chapter 5. And the objectives for this lesson are to describe an electron cloud with the electrons arranged according to Bohr's energy levels. And number 2, to describe how the Bohr model of an atom can explain the existence of atomic spectra. And number 3, explain the limitations of the Bohr model and why the Bohr model eventually ended up getting replaced by new and improved models of the atom. Let's get to it. Okay, so before we get into the Bohr model, you have to understand the problem that they were facing. They knew that we couldn't describe the movement of electrons around the nucleus the way that Rutherford envisioned, because when they did the math, the electron should just crash into the nucleus and the atom would explode, and it wasn't going to be a stable situation.
The physics behind that is as a charged entity goes around another charged entity, it actually would emit energy as it's going around its orbit.
Spirals inward, and
eventually, as you lose energy, the electron couldn't stay out in its orbit, and the electron would crash into the nucleus.
So for people that worry about such things, like physicists and chemists, that was a problem. We had to have a better model that could account for all that. And Bohr started by investigating why do elements like hydrogen only emit certain emission spectrum, or only absorb preferentially certain energies of light. And that was kind of the thinking that got him started on his model for electron behavior.
And just to once again, I think Bohr was actually the student of Rutherford.
I believe he was.
So we have one student correcting the next
teacher.
Yeah. So we started with Thomson, whose student was Rutherford, and then Rutherford, whose student was Bohr. I don't think the student of Bohr did the quantum model, but I'm not sure.
No, that came out, I don't think so anyway, but it was, it all, scientists build on one another's work, I think, is the thing that we're seeing.
All standing on the shoulders of giants.
Right, which is a quote by somebody, I don't remember who.
Yes.
But let's get on to the Bohr model. So this is a very busy slide, first of all, but we decided to kind of show you everything. But we're going to kind of point out what's important about the Bohr model.
Most of this should be written down, too.
This diagram would be the first thing I would write. And if you need to pause the video to do that, that is fine. And then I would copy down these 5 points about the Bohr model. And then what Mr. Hunter and I are going to do is kind of discuss each of these things point by point. And then we're also going to reference these other 2 diagrams as we go. But I think that the simplest one, the ladder diagram, is a good starting point.
Now, I don't think we should have you. I don't think you should copy down this diagram here. It's something you should be noticeable or be fluent with, or at least recognize. But this model over here might be something you want to do a general drawing for. So you draw basically a nucleus, and then around that you would draw a small circle and another small circle and another small circle, and label them n equals 1 for the first circle, n equals 2, 3, 4, and 5. And that way you can understand some of the math we're probably going to be doing later with these.
Right.
All right, so first let's start off with number 1 here.
So Bohr decided he had to think outside the box and come up with a new set of rules to explain the behavior of electrons, because the physics that they had didn't explain it.
Classical physics couldn't do this, so they came up with quantum physics, which deals with quantized energy levels for electrons in this case.
That was the first aha that Bohr had, is he said, let's imagine that the electrons can only occupy certain quantized energy levels. And so on our ladder diagram, being on the floor would be the first quantized energy level, and that has the quantum number n equal to 1.
Yes, and quantized, for those who don't means a specific amount. It's a certain amount of it, and in this case we're talking about energy, so each level has a certain amount of energy, no more, no less.
Just that amount. So n equals 1 is the lowest. That corresponds to a fixed amount of energy.
Also known as the ground state for us.
And the second point, go ahead, Mr. Hunter.
It says electrons are normally in their ground state. Sorry, I kind of jumped the gun on that one.
So an electron on a hydrogen atom would normally be sitting here
at n equals 1
in its ground state. or on this diagram it would be somewhere in this first little ring here, and it could stay there indefinitely and never gain or lose energy as long as it stayed on that level.
Nothing acts upon it as well.
Right.
So the third one, it says electrons can absorb a photon and jump to a higher energy level.
So if this electron's sitting here at its ground state and minding its own business,
all of a sudden another photon comes in and hits it.
It can jump up here to maybe the fourth level, and it's going to be stable for at least a short time on that level.
Stable for a while at least.
On that level. But it can't jump 3.5 rungs.
Yeah.
Just
so the
like
energy it's hit with has to be exactly the right amount to jump it from one ring to another, or one level to the next.
So here on the ring diagram, it would be down here at n equals 1. And it's going to jump out here to n equals 4.
Yeah.
And now it's on this ring here.
And if it's hit by light that's 3.5, it will not jump 3.5. It can only jump the 3, or it might not jump any.
So this electron, what do we call this electron that's now above its ground state, Mr. Hunter?
Be the excited state.
So it's in an excited state, and what's going to happen to this electron?
Well, like all things, it kind of runs out of excitement, and it will emit its photon that it absorbed, and it'll come out as usually a color in most of our cases, but it'll emit that and go back down to a ground state.
So it's going to drop back to the ground state, and a photon's going to zip off into space.
Now, another side note is it may not drop from the excited directly down to the ground.
That's
it might
true.
go stepwise. It might go here to here, then here to here, then here to the bottom, and it would emit different colors along the way. And that's actually one way how people make lasers, by having the emission of these things, but that's something I learned in grad school, and I can't even pretend to understand it all the way.
But what he began to do was track the energy on each level, and then with the help of some other scientists that did the work, they were able to identify, well, here, let's look at, these are all from an outer level over here back to the n equals 2 state. And they realized any time an electron jumps from a higher level down to the second level, a visible photon is emitted. So these are the exact jumps that give us the visible emission spectrum of hydrogen. So when it's on the third energy level, n equals 3, and the electron drops to n equals 2, you get this red photon emitted, which is this red stripe. And if it's on n equal to 4, and it drops back to n equals 2, that's a higher jump. Okay, and so the energy of the photon you get is going to equal the energy difference between the levels. So 4 is a higher energy state than 3. So when we jump from 4 back to 2, that's going to give us a photon of higher energy, which would be higher frequency,
higher energy,
and shorter wavelength. That's this blue band right here.
And then lastly, there's another band there somewhere.
We got violet, would be when we go from 5 down to 2, which is an even bigger jump. That would be this violet band here, which is even higher energy and frequency.
So now if we want to jump back to our first lesson where we had you look at that electromagnetic spectrum, it makes sense that a red light would have the lowest energy associated with it because it's only jumping one level. And then if we jump up to a teal or blue color, because we know Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, that the blue would have to have more energy because it's higher on the energy scale, higher on the frequency. So this is where those lights actually come from. The difference in these gaps, or n equals 1, n equals 2, n equals 3, the more gaps that they jump, or the more energy levels that they jump, the more energy they contain, which means the higher frequency, the different color, and different wavelength. So we can start applying the equations we already learned from the first part to this, and we can start asking you to solve for what color you would expect a certain element to emit if it jumps from one energy level to another.
So while we're talking about jumps, then you will see this energy level diagram represented this way, where instead of a circle, they have a series of lines. Okay, and here's n equal to 1, 2, 3, and you can notice as we go up, the difference in energy gets less between them. The biggest jump is between 1 and 2. But Bohr had all this mapped out, and they were able to make some predictions. Well, there should be energies of invisible light given off from some of these other jumps then, based on the energy differences. And you notice that these all have names: Fund series, Passion series, Bracket series, Lyman series. These are the scientists that actually went out and investigated Bohr's predictions. And in fact, Lyman found out that the energy changes predicted by Bohr, and it dropped from 8 to 1 or 7 to 1, 6 to 1, 5 to 1, etc., all gave different distinct wavelengths of ultraviolet light. And Brackett, Passion, and Fun found the same thing. Jumps from 8 to 3, or 7 to 3, or 6 to 3, or 5 or 4 to 3 gave infrared. Passion investigated infrared also and found that jumps from a higher level to the 4th level gave infrared, and so on with the Fun series. So the Bohr model did what a good model should do, and that is it enabled predictions. It had a predictive quality to it. We could predict energies that should come from these different jumps from one level to another based on the energy levels that Bohr had identified.
And there is one last thing we should point out. Like I said, we're going to tell you how to calculate colors based on what we're talking about. So if we look at this one again, you can look right here and see delta E equals HV. And at the very end, you see 1 over n squared 1 minus 1 over n squared 2. That's saying that is the jump from one level to another. And that we can use to calculate the energy, and we can plug it in here to calculate wavelength, frequency, energy, everything we want. So, I mean, there's a lot of information being thrown at you right here, and we're going to have a lot of practice with it here very shortly.
But I think that the basic idea is the 5 points in your notes there, and that's you know, in a non-mathematical way, we're trying to explain the Bohr concept. The biggest change being from classical physics that this idea of compartmentalized or quantized energy, as long as an electron stays on a given level, it doesn't gain or lose any energy. It has a fixed amount of energy, and there's a higher fixed amount of energy associated with each higher level. Jumps between levels correspond to certain energy either being absorbed or emitted depending on whether the electron is jumping up. It needs to absorb a certain quanta of energy, or when it goes down a level or goes down 2 levels, it emits a certain quanta of energy. And that's the beginnings of our understanding of the quantum atom. Energy and absorption of energy appears to be compartmentalized and quantized. 10 minutes on this slide, Mr. Hunter. Holy cow.
Next slide is be the last slide.
So we know we've been talking about models. For a scientific model to be valid, it has to account for all known observations. It has to be consistent with everything we already know to be true, and it needs to be workable, or that is predictive of something in the
properties.
future.
So one of the things that the Bohr model did do was prevent the electrons from crashing into the nucleus.
Okay, so it was a good model.
That's a good model.
And it enabled them to predict, okay, certain jumps of energies should correspond to certain visible, invisible frequencies. They tested all that, worked great.
I guess the question is, where are the shortcomings?
Right. So in the long run, the Bohr model was not considered a workable model because of one major flaw. It only worked for atoms with 1 electron.
These are also known as hydrogen-like atoms. If I had a uranium, which is the atomic number 92, it has 92 electrons. Bohr's model would not work. But if I took off 91 of those electrons,
then it would
then work. And you could
the problem is most uranium atoms
do not like giving up 91 electrons.
Of their electrons. Okay, so that's a big problem, and that's something that the next generation of scientists had to work on to figure out. Okay, he's on to something here with this quantum idea, but the simple imagining of these little rings of energy around the atom wasn't quite it. And it took some really excellent mathematicians to kind of look at the problem and to come up with, well, what are the solutions that would enable us to predict other circumstances. And when you have multiple electrons around the same atom. And so that's where we're going to move into next, looking at the modern concept of the quantum atom. So, but Bohr gave us it's a good start. Let's say that's a good start. And like Mr. Hunter said, we still, even though we know that model is not completely 100% correct, Will. The most common depiction of an atom in a chemistry class is as a Bohr atom with little rings that represent different energy levels and different number of electrons on each ring. So even though we know that's not quite 100% accurate, it's a useful model for us to picture things.
Yeah, it's useful for us to help teach. All right, well, we'll get some practice with this as well, and see you tomorrow.
All right, so post-video questions. Number 1, explain how the Bohr model accounts for absorption and emission spectra for hydrogen atoms. How does the Bohr model explain the existence of the distinct absorption and emission spectra? Question 2, what were the limitations of the Bohr model, and why did it have to be replaced? What did it fail to do? So see what you can do with those, and we will discuss them when we meet again.